Humanity's next home might be a hollowed-out mountain flying through space. This is the radical engineering required to hollow out asteroids for human habitation, a challenge that redefines survival itself. By the end of our journey, you will understand exactly how we could turn a tumbling space rock into a thriving, self-sufficient world. We will confront the puzzles of containing catastrophic collapse while carving out caverns, and ask what it takes to build a society sealed inside solid stone. This future hinges on solving problems we are only beginning to grasp. What does a civilization look like when it is built from the inside out? The first step is not about building, but about choosing. Our entire future hinges on selecting the perfect cosmic quarry, a single space rock from millions of candidates. This choice is far more complex than simply picking the biggest or the closest. It requires a careful balance of composition, size, location, and hidden structural secrets. Get this wrong, and you are not just setting back a project, you are potentially dooming it before a single tool is deployed. Composition is everything. We are not looking for just any asteroid. We are searching for a specific class known as Carbonaceous chondrites. These are the treasure troves of the solar system, dark, primordial bodies rich in the very materials we need to survive. They contain water locked away in clay minerals and hydrated salts, which can be extracted for drinking, growing plants, and broken down into breathable oxygen and rocket fuel. They are also packed with organic compounds, the building blocks of life, and valuable metals like nickel and iron. An asteroid of the wrong type, like a dry, metallic one, would force us to haul every single drop of water and molecule of air from Earth, an impossible logistical and economic burden. The right rock brings its own life support kit. Size is a delicate equation, too small, and you cannot carve out enough usable space for a sustainable population and infrastructure. Too large, and the sheer scale of the excavation becomes a multi-generational nightmare, overwhelming our initial engineering capabilities. The sweet spot, according to most conceptual studies, lies in the range of several hundred meters in diameter. Picture a mountain, but one floating in the void. This provides a massive volume of material, potentially creating living spaces larger than any city on Earth, while still being a target we can realistically approach and begin to work on within a human lifetime. Then there is the orbit. A perfect asteroid in a terrible location is useless. We need a stable, predictable path around the Sun, one that does not swing too close to Earth or plunge too deep into the outer solar system, extremes that would demand catastrophic amounts of energy to reach or leave. More importantly, its orbit should be relatively accessible, what mission planners call a low delta-V trajectory. This minimizes the fuel needed for spacecraft to rendezvous with it, a critical factor when every kilogram launched from Earth costs a fortune. The ideal candidate is not just a resource-rich body, but one conveniently parked along a celestial highway we can regularly travel. But perhaps the most critical and most hidden factor is structural integrity. Many asteroids are not solid chunks of rock. They are what scientists call rubble piles, loose aggregations of boulders, dust, and gravel held together by nothing more than their own minuscule gravity. As planetary scientist Dr. Amanda Hendricks often highlights, understanding this internal architecture is paramount. If you start drilling into a rubble pile without reinforcing it, you could trigger a catastrophic chain reaction, causing the entire structure to collapse in on itself. It would be like trying to hollow out a pile of sand. So, before any excavation, we must use radar, seismic probes, and other remote sensing tools to map the asteroid's interior, identifying stable layers and potential fault lines. This invisible geology will determine the safety of every corridor and chamber we create. Choosing the right asteroid is not an opening act, it is the entire foundation. With this cornerstone selected, the radical engineering truly begins. Securing this chosen mountain is an act of cosmic Parker. Our target is not a stationary world with a firm surface and steady gravity. It is a tumbling, irregular object drifting in a silent sea of microgravity. The first and most delicate operation is simply making contact without bouncing off or shattering the fragile structure. This requires tools that seem more suited to deep-sea fishing or high-stakes salvage than space engineering. One leading concept involves firing harpoons not to kill but to anchor. These specialized tethers would penetrate the surface and deploy expanding anchors within the asteroid's regolith, creating multiple strong attachment points. Another approach uses large, flexible nets cast by a spacecraft to envelop a section of the asteroid, distributing force and providing a web of connection points for robotic arms and tools. The goal is a gentle, multi-point embrace, latching onto the rock with enough stability to begin the next critical phase without causing any disruptive shock. With a secure grip established, the real transformation begins, starting with motion. A tumbling asteroid is useless for habitation, its chaotic spin making any internal construction impossibly dangerous. We need to impart a controlled, steady rotation, a deliberate spin that will eventually create the artificial gravity needed for life inside the hollowed shell. This is not a quick maneuver. Using solar-powered ion thrusters or mass drivers attached to the surface, engineers would apply a tiny, continuous force over months or even years. Think of it as pushing a colossal, floating boulder with the gentlest, most persistent breeze imaginable, slowly nudging it into a perfect, stable pirouette. The calculations here are phenomenally precise. Spin it too fast, and centrifugal forces could exceed the asteroid's own meager gravitational cohesion, literally tearing it apart from the inside out. Every calculation depends on the detailed internal model created during the selection phase, understanding exactly how much stress the conglomerate of rock, metal, and ice can withstand. This meticulous process of spin stabilization does more than just stop the tumble. It fundamentally changes the nature of the object. The wild, unpredictable rock becomes a controlled, rotating platform, a construction site with a defined up and down. It is the essential precondition that makes all the interior engineering not just possible, but predictable, setting the physical stage for the monumental task of carving out a world from within. But how do you actually carve a home from that stabilized stone? The methods proposed are less like traditional construction and more like a form of cosmic sculpture, split between two radically different philosophies. The first is aggressive and direct, a strategy of mining. Picture fleets of autonomous robotic excavators clinging to the interior walls of a drilled pilot tunnel. They would use cutting lasers to slice through rock or controlled pulses of energy to fracture material, methodically chewing out vast caverns. Every ton of excavated rubble is not waste, it is a resource. This processed material could be sintered by focused sunlight into solid bricks for interior structures, or strategically relocated to form a thick, outer layer of radiation shielding around the living spaces. It is a brute force approach that offers immense control over the final shape of the caverns, but demands enormous amounts of energy and time, essentially disassembling the asteroid piece by piece. The second philosophy is far more subtle, a technique of gentle persuasion known as inflation. Proposed by thinkers like aerospace researcher Dr. David Gump, this method works with the asteroid's own structure. Engineers would first drill a narrow access shaft to the center of the spinning rock. Then, they would insert a colossal, incredibly durable inflatable structure, a bladder made of advanced polymers or flexible composites. Once in position, this bladder would be slowly pressurized, expanding with steady, immense force. Instead of carving the space out, the pressure fractures the surrounding rock from the inside and pushes it outward, compacting the material against the asteroid's own spin-induced gravity to form a dense, thick shell. It is like blowing up a balloon inside a ball of clay, the clay itself becoming the vessel. This method could be significantly faster and less energy-intensive than mining, as it uses the asteroid's mass against itself. However, it surrenders precise control over the interior geometry. You get the shape the pressure creates, and it relies entirely on the structural integrity of that newly formed shell. The choice between mining and inflation is not just technical, it is foundational. It will define the very character of the habitat and the timeline for its creation. A mined cavern could have cathedral-like vaults and precisely engineered support columns, shaped for optimal community layout and airflow. An inflated shell might result in a more organic, pod-like interior, its architecture dictated by the physics of pressure and fracture lines. One approach is a deliberate, granular act of creation. The other is a catalyzed transformation. This decision influences everything, from the psychological feel of the living spaces to the long-term stability of the habitat against micrometeoroid impacts or internal stresses. It asks whether we are builders who assemble or gardeners who encourage growth, a fundamental question of how humanity will shape its first permanent homes beyond Earth. The act of carving, whether by mining or inflation, creates a silent, pervasive enemy. In the airless void, every chip of rock and mote of dust liberated from the asteroid's surface becomes a permanent, free-floating hazard. Without an atmosphere to settle it, this excavation debris forms a perpetual, abrasive cloud, a fog of microscopic shards that can sandblast solar panels, clog delicate machinery joints, and pose a severe risk to any astronaut or robot working outside. Furthermore, in the sun's intense light, these tiny particles can become electrically charged, sticking stubbornly to viewports and sensitive instrument lenses like static charged glitter. Containing this chaos is not a secondary cleanup task. It is a primary, continuous engineering system that must operate from the very first cut. One elegant solution leverages the dust's own properties. Since many particles carry an electric charge, strategically deployed electromagnetic fields could act as invisible walls, corralling the debris into designated containment zones. Picture a magnetic funnel, gently guiding the hazardous cloud away from work areas and toward collection points. There, robotic sweepers equipped with adhesive surfaces or gentle suction could gather the material. But the most powerful approach transforms this problem into the project's greatest asset. Instead of merely storing the debris, we process it. The collected dust and rubble can be funneled into automated processing plants, where focused solar mirrors or microwaves sinter the material, fusing it without melting into solid, ceramic-like blocks. These blocks become the literal building blocks of the new world inside. They can be assembled into interior walls, floors, and support structures, or transported to the habitat's outer layer to add meters-thick radiation shielding. This closed-loop system means the very act of creating space simultaneously provides the material to fill that space with infrastructure. The management of debris, therefore, shifts from being a costly nuisance to the central supply chain for construction, turning the asteroid's own substance into its new skeleton. Every speck of dust becomes a potential brick, and every fragment a piece of the puzzle, ensuring nothing is wasted in the meticulous craft of building a home from the inside out. The cavern is carved, but it remains a fragile void. A hollowed asteroid is not yet a habitat, it is a cavity under immense and conflicting pressures. Inside, the air we need to breathe pushes outward with the force of an entire atmosphere. Outside, the centrifugal force of the habitat's spin pulls the structure apart, while the constant whisper of micrometeoroids threatens to puncture it. The crude rock wall left by excavation or inflation is porous, fractured, and utterly unreliable for containing a world. To survive, we must forge an inner shell, a perfect, seamless barrier between the living space and the lethal vacuum. This is the moment we transition from miners to architects, building a vessel within a mountain. The first challenge is sealing the countless microscopic pores and fractures in the rock itself. One elegant solution uses the asteroid's own substance as the sealant. Imagine robotic platforms moving like cautious spiders across the vast interior curvature. They are equipped with high-temperature torches or focused solar concentrators that can process excavated rubble on the spot, melting it into a molten ceramic or glassy slag. This material is then sprayed onto the walls in a continuous, overlapping layer, much like applying a thick, incredibly durable coat of glaze to a giant pottery vessel. This sprayed-on liner fuses with the underlying rock, creating a monolithic, airtight seal that is chemically identical to its substrate, preventing problems with differential expansion. It is a form of artificial geology, creating a new, impermeable layer where one did not exist. Yet a sealed shell is not necessarily a strong one. To withstand the relentless stresses of spin and pressure, the habitat needs reinforcement, an internal skeleton. This is where nanotechnology and autonomous robotics converge in breathtaking fashion. Swarms of 3D printing drones no larger than your hand could take to the cavern. Their task is not to add mass but to weave strength. They might deposit threads of carbon nanotubes, each many times stronger than steel by weight, or extrude fibers spun from the asteroid's own basalt. These fibers would be laid down in a precise, geodesic grid, a web of incredible tensile strength bonded directly to the sprayed liner. This composite mesh acts like the rebar in concrete, absorbing tensile forces and distributing any point of impact across a wide area of the shell. It turns a brittle ceramic bowl into a flexible, resilient composite structure. The engineering of this reinforcement grid is a ballet of applied physics. The pattern cannot be uniform. It must be meticulously calculated based on a dynamic stress map of the entire rotating habitat. Areas under the greatest strain, such as the equator of the spinning cylinder, would receive a denser weave of fibers. Points where internal structures like support columns or utility conduits connect to the shell would be specially reinforced to distribute their load. This digital skeleton, woven into the very fabric of the walls, is what prevents a tiny crack from propagating, a small impact from becoming a catastrophic rupture. It is a silent, intelligent nervous system for the shell, constantly managing the forces that threaten to tear it apart. This process, the forging of the inner shell, is the definitive act of creation. It transforms the project from an excavation into an embodiment. That rough-hewn cavern becomes a pressurized vessel, a container for an atmosphere and ultimately for a society. The strength of this fabricated barrier does not just hold back the void, it defines the safety, the longevity, and the very possibility of everything that comes next. With this secure inner world established, the focus can finally turn inward to the question of what fills that protected space. The sealed shell now holds a perfect, silent vacuum, a blank canvas for the most delicate engineering of all. We must fill it with a bubble of Earth, not as a static supply, but as a living, breathing, self-renewing process. This is the heart of the habitat, a closed-loop system of such intricate interdependence that a single failure in one circuit could unravel the entire delicate web of life. Unlike a spacecraft carrying all its supplies, an asteroid colony cannot rely on resupply from home. The distances and costs are far too great. Its survival depends on achieving what our own planet does effortlessly, recycling every molecule of air, every drop of water, and every bit of organic matter with near-perfect efficiency. The first circuit is the air we breathe. Human lungs take in oxygen and exhale carbon dioxide, a simple exchange that becomes a deadly accumulation in a sealed space. Traditional chemical scrubbers can manage this for a time, but for permanent habitation, we turn to biology itself. Vast algae bioreactors, illuminated by full-spectrum LEDs tuned for photosynthesis, become the colony's lungs. These dense green cultures consume the carbon dioxide we exhale and, using energy from light, convert it back into precious oxygen. But the algae are more than just air scrubbers. They are a foundational crop, rich in proteins and nutrients that can be harvested for food or processed into base materials. This integration transforms a waste product into a vital resource, closing the first critical loop. Water is the next sacred cycle. Every use, from drinking and hygiene to the humidity in the air and the irrigation of plants, must be part of a relentless recovery process. The system begins with the asteroid's own locked-away water, extracted and purified. Once in use, it journeys through a multi-stage reclamation process that would put any earthly city to shame. Advanced filters remove physical contaminants, while biological processors use carefully selected microbes to break down organic waste. The final stage often involves distillation or vapor compression, using the habitat's own waste heat to boil and recondense water into a state of purity exceeding most natural sources. Not a single molecule is willingly lost. The goal is to recover over 99.9% of all water introduced into the system. This creates a perpetual internal hydrologic cycle, a miniature version of Earth's clouds, rain, and rivers, all contained within pipes and tanks. Food production cannot be an afterthought. It is a core life support function. Expansive hydroponic and aeroponic farms will line illuminated tiers within the habitat, their roots misted or submerged in nutrient-rich solutions derived from recycled biological waste. These are not soil-based farms, but precisely controlled environments where light, temperature, and nutrient delivery are optimized for maximum yield in minimum space. Crops are chosen not just for nutrition, but for their role in the larger system. Fast-growing leafy greens for oxygen production, legumes for fixing nitrogen, and staple grains for caloric density. Even inedible plant matter is returned to the processing system, its nutrients extracted to begin the cycle again. The true complexity, however, lies not in any one of these systems, but in their interconnection. The oxygen from the algae farms supports the humans who tend the crops, whose waste feeds the bioreactors that clean the water used to irrigate those very same farms. It is a dance of constant dynamic balance, a miniaturized systems ecology that must remain stable for generations. Redundancy is not a luxury, it is the law. Every critical component will have multiple backups, and the design philosophy must allow for graceful degradation, where the failure of one subsystem triggers others to compensate, rather than causing a catastrophic collapse. Designing this closed-loop heart is the ultimate test of our understanding, requiring us to become stewards of a world we built from scratch. It asks if we can truly replicate, within an armored shell, the enduring cycles that have sustained life on our home planet for eons. A sealed, self-sustaining shell is still not a home. It remains a sterile environment, a potential trap for the human body and mind, unless we can recreate the two most fundamental sensations of life on Earth, the steady pull of gravity and the simple act of breathing fresh air. These are not amenities, they are biological necessities. Prolonged exposure to microgravity weakens bones and muscles, confuses the inner ear, and causes fluids to shift unnaturally in the body. To build a permanent society inside an asteroid, we must engineer the very forces of nature, spinning the entire habitat to create a stable down and filling the colossal cavern with a sky. Creating artificial gravity is a feat of precise celestial mechanics. The principle is straightforward: spin a cylindrical habitat, and centrifugal force will push inhabitants outward against the inner wall, which becomes the floor. But the engineering is a delicate balance. The goal is to replicate Earth's gravity, what scientists call 1G, without inducing debilitating side effects. The spin rate and the radius of the habitat are locked in a critical equation. Spin too slowly with a small radius, and the Coriolis effect becomes overpowering. This subtle force, the same that influences weather systems on Earth, would make simple actions feel bizarre. Tossing a ball to a friend would see it curve dramatically in the air. Pouring a drink would see the liquid spiral as it falls. More critically, the difference in gravitational pull between your head and your feet could be significant enough to cause dizziness and nausea. To minimize these effects, you need a large radius, a truly vast interior space. For a comfortable 1G environment, conceptual designs suggest a habitat cylinder at least several hundred meters in radius, spinning at a gentle, almost imperceptible rate of perhaps 1 revolution every minute or two. This creates a stable, uniform force field where up is toward the central axis and down is firmly against the curved outer shell, allowing life to feel reassuringly normal. Simultaneously, engineers must perform another act of planetary scale engineering on a miniature scale, crafting an atmosphere. Filling millions of cubic meters of volume with a breathable mix of nitrogen and oxygen at Earth standard pressure is a monumental logistical task, initially supplied by processing the asteroid's own ices and minerals. But simply having the right gases is not enough. The atmosphere must be alive. In a rotating habitat, air is not a passive blanket. It is a dynamic fluid subject to the same Coriolis forces. Without careful management, the spinning motion would stratify the atmosphere, creating thin, still layers and preventing proper mixing. Stale air could pool in certain areas, while others might become drafty tunnels. The solution is a meticulously designed ventilation system, integrated into the very architecture of the interior landscape. Vents, ducts, and convective flows would be engineered to work with the rotation, ensuring a gentle, planet-like circulation that distributes heat, removes excess humidity, and delivers fresh air to every corridor and chamber. This constant, subtle breeze is vital. It prevents pockets of carbon dioxide from building up around sleeping inhabitants and carries the sense of soil and plants from the agricultural tiers, providing the sensory background of a living world. The ultimate test of this engineered environment is not on a schematic, but in human experience. Success means a child born in the habitat can run without stumbling, where trees grow straight toward the artificial sun along the central axis, and where the air in your lungs feels indistinguishable from that of a forest on Earth. It is the profound achievement of making the utterly artificial feel completely natural, granting inhabitants not just survival, but the psychological foundation for a thriving, grounded society. This careful replication of gravity and atmosphere is the final gift of engineering, the stage upon which daily life, with all its ordinary wonders and challenges, can finally begin. Deep within this armored mountain, the final frontier is not space but perpetual darkness. Sunlight, the universal rhythm of life, cannot pierce hundreds of meters of solid rock. Without it, the habitat is just a buried tomb. Illuminating this interior abyss is therefore the ultimate act of bringing a world to life, a challenge that blends physics, biology, and profound psychology. It begins with a simple, non-negotiable human need, the day-night cycle. Our bodies and minds are tuned to the rising and setting of the sun, a rhythm embedded in our very cells that governs sleep, hormone release, and overall well-being. To deny this cycle is to condemn inhabitants to a state of permanent jet lag, disrupting sleep, impairing cognitive function, and eroding mental health over time. The lighting system, therefore, must be a faithful clock. One elegant solution looks not to generate light, but to steal it. Engineers could construct massive light wells, essentially giant tubes lined with perfectly aligned mirrors that channel real sunlight from collectors on the asteroid's sunward surface. This captured light could then be piped down through bundles of optical fibers, diffused at the end into broad, gentle panels that span sections of the central axis, acting as artificial suns. This direct solar light would provide the most natural illumination possible, its intensity and color temperature shifting subtly throughout the habitat's artificial day, from the warm gold of morning to the bright white of noon and the deep oranges of evening. It is a literal thread connecting the interior society to the actual star at the center of our solar system, a psychological tether to the cosmos outside their stone shell. Yet, reliance solely on piped sunlight has a vulnerability. The asteroid's own rotation and orbit will periodically plunge the external collectors into shadow. Furthermore, the immense agricultural tiers will require far more consistent and intense light than what natural sunlight alone can provide over a 24-hour cycle. This is where supplemental artificial lighting takes over, a symphony of full-spectrum LEDs. These are not simple bulbs, they are tunable ecosystems of photons. For the farms, lights can be optimized for photosynthesis, bathing the plants in specific wavelengths that maximize growth. In living quarters, the light can be adjusted to support concentration, relaxation, or social interaction. The most advanced systems could even program seasonal variations, gradually shifting the color and duration of light throughout an artificial year to provide a sensory passage of time, preventing the feeling of being stuck in an endless, monotonous present. The placement and quality of this light becomes a foundational element of architecture and community design. Wide, open plazas might be bathed in the direct glow of a central light well, creating vibrant public spaces that feel connected to an open sky. Narrower residential corridors might use softer, indirect lighting to promote calm and privacy. The goal is to avoid the flat, uniform glare of an industrial facility and instead create a landscape of light and shadow, of bright communal areas and cozy, dimly lit niches. This careful choreography does more than just let people see. It directly shapes mood, productivity, and the very perception of space. A well-lit habitat feels expansive and alive. A poorly lit one feels claustrophobic and oppressive. In this way, the engineers of light become the artists of atmosphere. They are painting with photons, defining the emotional palette of an entire civilization. The gentle dawn that washes over the agricultural tiers, the sharp clarity of light in a research lab, the warm glow from a residential window in the evening, these are not just technical outputs. They are the crafted experiences of a normal day, the subtle, constant reassurance that life here, though engineered down to the photon, can still feel beautifully, fundamentally real. But a living, breathing world also needs a steady, unfailing pulse. Every breath of recycled air, every photon of artificial sunlight, and every turn of a manufacturing robot demands a constant torrent of energy. Isolated by millions of miles from any planetary power grid, this civilization in a rock must become a master of generating, storing, and managing its own energy with absolute reliability. Its power architecture cannot be an afterthought. It is the uninterrupted heartbeat that keeps the entire system alive. The most straightforward source is the sun itself. The asteroid's barren, airless surface is a perfect platform for solar energy, free from clouds or atmospheric scattering. Engineers could deploy vast, lightweight arrays of thin-film solar panels, unfolding like shimmering wings across the rocky landscape. To maximize exposure, they might even construct a constellation of solar power satellites in a close orbit around the asteroid, beaming energy down via concentrated microwaves or lasers to receiving stations. This provides a clean, abundant source of power, but it comes with a fundamental vulnerability. The asteroid's own rotation and orbit will plunge it into shadow for long periods, creating a desperate need for energy storage on a staggering scale. For baseload power, the kind that never flickers, the colony may need to look inward to the very atoms of its home, compact, sealed nuclear fission reactors using fissile materials like uranium or thorium potentially mined and refined from the asteroid's own composition could provide a dense, relentless source of heat and electricity for centuries. These would not be the massive complexes of Earth, but rugged, passively safe units designed for deep space, buried within the habitat's shielding for safety. Further on the horizon lies the dream of fusion power, mimicking the Sun's own engine. If this technology matures in time, an asteroid rich in deuterium from its water ice could become a self-fueling powerhouse, offering nearly limitless energy from a few grams of fuel. Yet, regardless of the primary source, storage is the linchpin. Advanced battery banks using novel chemistries could hold charge for the habitat's night cycle. More mechanically elegant solutions might involve flywheels spinning at incredible speeds in vacuum chambers, converting electricity into kinetic energy and back again with minimal loss. Another robust method uses thermal storage, where excess solar energy is used to heat a reservoir of molten salt or ceramic blocks during the day, with that heat slowly converted back to electricity via turbines when the sun is gone. The true genius of the system, however, lies in its integration and redundancy. Solar panels charge the batteries and heat the thermal banks during the day, while the nuclear or fusion reactor hums along at a steady state, ensuring the life support systems never experience even a millisecond of interruption. Smart grids would dynamically route power, prioritizing oxygen generation and water reclamation over non-essential manufacturing the moment reserves dip. This energy network must be designed for graceful degradation, where the failure of one reactor or one solar array simply triggers others to pick up the load, preventing a single point of failure from cascading into darkness. The power flowing through these circuits is more than electricity. It is the physical manifestation of the colony's will to persist. It is the warmth in the air, the light on the leaves in the farms, and the signal carrying a child's laugh from one corridor to the next. Designing this heartbeat requires a cold, logical assessment of risk and abundance, but its purpose is profoundly human, to ensure that the world inside the rock never, ever sleeps. Yet this carefully crafted interior world faces a silent, invisible siege. Beyond the thick rock walls, space is not an empty void but a storm of radiation, a relentless downpour of high-energy particles from the sun and distant stars. An asteroid's natural bulk provides a good start, but it is not a perfect shield. Creating a truly safe long-term home demands a deliberate, multi-layered defense. A cosmic armor designed to absorb both the unseen rays and the occasional speeding grain of sand that could pierce a spacesuit. The first and most powerful layer is simply mass. By positioning all living quarters, farms, and critical systems deep within the core of the asteroid, engineers use the mountain itself as a barrier. Hundreds of meters of solid rock and processed regolith overhead become a natural ceiling against cosmic rays, attenuating their intensity to levels comparable to a low-altitude city on Earth. It is the same principle as taking shelter in a cave during a storm, using the planet's own body for protection, but we can enhance this natural barrier. One of the most effective materials for stopping radiation is hydrogen, and water is full of it. Engineers might design a secondary shield by installing water-filled bladders or tanks as lining for the outermost living spaces, turning the habitat's vital water reserves into a functional part of its defensive architecture. Alternatively, processed rubble from the excavation could be robotically piled into massive berms over key areas of the outer shell, adding meters of extra, free shielding material. For the more sudden, visible threats, the strategy shifts. Micrometeoroids, tiny fragments traveling faster than a rifle bullet, pose a puncture risk. The solution here is not to try and stop them with a single thick wall, but to outsmart them. Around the most vulnerable external components, like docking ports or sensor arrays, engineers would construct a Whipple shield. This ingenious design uses a thin, sacrificial outer bumper, spaced several centimeters away from the main habitat wall. When a high-speed particle strikes this outer sheet, it vaporizes on impact, spreading its energy into a cloud of gas and debris that then harmlessly splatters against the primary wall. It turns a single, dangerous bullet into a harmless puff of plasma, using clever spacing and material science to dissipate a tremendous amount of kinetic energy. This integrated shield system, combining the asteroid's mass, strategic water layers, and intelligent bumper designs, operates in perpetual silence. There are no flashing lights or alarms when it works perfectly, only the profound quiet of safety maintained. It is the ultimate expression of precaution in a hostile environment, ensuring that the society growing within this rocky fortress is sheltered not just from the emptiness of space, but from its invisible, energetic fury. With this durable sanctuary secured, the focus can finally turn from pure survival to the shape of the society that will grow there. The ultimate challenge of this engineered world is not physical, but psychological. How do you design a society to thrive when every horizon is a curved wall of solid rock? The architecture of confinement must become an architecture of liberation, transforming a sealed cavern into a place that feels not like a shelter but a true home. This demands a philosophy that prioritizes human perception and well-being as its core engineering specifications. The first principle is to shatter the cave illusion. Instead of a single, cavernous hollow, the interior would be sculpted into a tapestry of diverse spaces. At its heart would lie a vast central atrium, a vertical city park stretching from the residential levels on the outer shell all the way toward the central axis. This is not just an open space, it is a manufactured skyline. Tiered balconies brimming with hanging gardens, cascading waterfalls recycled from the habitat's water systems, and winding footpaths would create a layered, living landscape. The far wall, the opposite side of the cylinder, would not appear as a distant ceiling but as a panorama. Using projected imagery, massive light panels, and perhaps even vast curved screens, it could display a dynamic, ever-changing vista. One day, it might show a real-time feed from cameras on the asteroid's surface, a breathtaking view of the star field and passing planets. Another day, it could cycle through simulations of earthly landscapes, a forest at dawn or an ocean sunset, providing a vital psychological connection to the sensory richness of a planetary environment. This manufactured horizon gives the eye a place to wander, a visual escape that tricks the brain into perceiving depth and distance where none physically exists. Within this grand scheme, the design of individual neighborhoods becomes crucial. Long, straight corridors induce a sense of monotony and confinement. Instead, pathways would curve gently, revealing new vistas around each bend, perhaps opening onto smaller, intimate plazas with bubbling fountains or community gardens. Clever use of mirrors, strategically placed and angled, could reflect light and scenery to double the perceived space, making a modest courtyard feel like a sun-drenched square. The lighting itself would be paramount, never flat or uniform. It would mimic the sun's journey with warmer tones in residential areas during evening hours and brighter, cooler light in communal workspaces, reinforcing the natural circadian rhythm that is so easily lost underground. Privacy in a community where everyone lives in close proximity is not a luxury but a necessity for mental health. Alongside the open atriums and parks, the architecture must provide a gradient of social spaces. Beyond the public square are smaller gathering nooks, and beyond those, the sanctuary of the private residence. These homes would be designed with acoustic dampening to ensure quiet, and while their outer wall is the habitat's shell, interior windows could look out onto private, enclosed gardens, or tranquil artificial light wells, giving each family a personal connection to greenery and light. The goal is to offer a choice: the vibrant energy of the community atrium or the peaceful solitude of a private terrace, allowing individuals to regulate their social exposure and find balance. This meticulous attention to psychological design is what separates a functional habitat from a civilization. It acknowledges that a society cannot be sustained by oxygen and calories alone, but requires beauty, variety, and the perpetual illusion of possibility. It asks the architects to become psychologists and the engineers to become artists, all collaborating to build a world where the spirit, not just the body, can truly belong. This self-sufficient world must also become an engine. Its survival depends on turning the very rock that surrounds it into the tools, the fuel, and ultimately, the wealth that secures its future. This practice is called In-Situ Resource Utilization, or ISRU, a technical term for the most ancient of human arts, living off the land. But here, the land is a floating mountain of primordial rubble, and mastering it requires an industrial revolution in miniature. The first and most precious resource is water. Locked within the clay and minerals of a carbonaceous asteroid, this water is not for drinking alone. It is the cornerstone of a new economy. Automated mining rigs anchored to the surface would use drills and heated probes to extract this ice, which is then purified and stored. The magic happens in electrolysis plants, where an electrical current splits the water molecules into their component parts, hydrogen and oxygen. These gases, when chilled to cryogenic temperatures, become high-performance rocket propellant. This means the asteroid habitat can refuel passing spacecraft, becoming a cosmic gas station along the interplanetary highway. More critically, it can fuel its own fleet of mining drones and transport vessels, enabling it to reach out and harvest resources from neighboring asteroids without relying on Earth for every drop of propellant. The oxygen, of course, also feeds directly into the habitat's own breathable atmosphere, closing another vital loop. But the asteroid offers more than just volatiles. Embedded within its matrix are rich veins of metals, primarily iron, nickel, and cobalt. To access these, the colony would deploy processing facilities that use a combination of techniques. Magnetic separators could sort crushed regolith, pulling out grains of metallic iron. For more complex ores, furnaces heated by concentrated sunlight could smelt the material, separating the pure metals from the rocky slag. These metals become the literal building blocks for expansion. They can be forged into structural beams for new modules, turned into wire for the expanding electrical grid, or alloyed into specialized parts for machinery and robotics. This allows the habitat to manufacture and repair its own infrastructure on site, moving from dependence on imported goods to true industrial autonomy. Even the leftover rocky material, the silicates, is far from waste. When heated in solar kilns, this common rock can be melted and spun into fine fibers to make asteroid-derived glass or sintered into tough, ceramic tiles for construction and radiation shielding. This comprehensive use of every gram of material transforms the entire operation. The habitat is no longer just a consumer of resources, it is a producer. It transitions from a closed-loop life support system to an open-loop economic engine. The propellant, metals, and manufactured goods it produces could be traded with other space-based outposts, lunar bases, or even missions heading to Mars. This trade would not be measured in traditional currency at first, but in essential commodities, energy credits, or shared technological advances. An asteroid that masters ISRU stops being a remote outpost struggling for survival. It becomes a hub, a source of genuine abundance and strategic value in the solar system's emerging economy. Its wealth is not shipped from Earth, it is forged from the stones of its own home, granting it a level of independence and purpose that redefines what a space colony can be. Within this sprawling interior landscape, movement itself becomes a designed experience. A habitat several kilometers across cannot function if crossing from a residential quarter to a distant agricultural dome feels like a day's journey. The solution is a multi-layered transit network, a kind of three-dimensional subway system that respects the physics of the spinning world. At the very center, along the rotational axis, lies a realm of calm. Here, the centrifugal force drops to almost zero. This axial corridor, a wide, tunnel-like space running the length of the cylinder, becomes the habitat superhighway. In this gentle microgravity, cargo pods and passenger capsules can be propelled with minimal energy, gliding silently on magnetic rails or pushed by gentle puffs of air. This is the primary route for moving bulk supplies between distant longitudinal sectors, or for personnel who need to travel from one end of the colony to the other without experiencing the full gravity of the outer shell. It is the spine of the entire system. Down on the curved inner surface where gravity holds firm, a different kind of transit emerges, running along the circumference just above the main architectural levels. A high-speed maglev loop provides rapid transit. Think of it as a train that never turns, continuously circling the world inside. Stations spaced at regular intervals would connect to neighborhoods, research hubs, and industrial zones, allowing someone to travel halfway around the habitat's interior in a matter of minutes. This circumferential line handles the bulk of daily commuter traffic, tying the disparate communities into a single, accessible loop. But for the space between the maglev stations and the front doors, a more human-scale system takes over. Winding through the tiered parklands and along residential avenues, networks of paths accommodate bicycles and small, quiet electric vehicles. These are not for long-distance travel, but for the last mile, for a leisurely ride through the central park or a quick trip to a local market. This slow transit layer is vital for community health and casual interaction, ensuring the habitat feels navigable on a personal, unhurried level. Freight, however, follows its own dedicated rules. Automated cargo trams would run on separate, subsurface tracks, delivering harvested food from the agricultural tiers to processing centers, or transporting raw materials from docking ports to manufacturing modules. This separation keeps heavy logistics invisible and silent, preserving the tranquility of the living spaces. The true genius of this network is its integration with the habitat's gravity gradient. Moving from the outer shell to the central axis is a journey of decreasing weight. Elevators or inclined transit tubes would not just move people vertically, they would gradually adjust their orientation as they climb, preparing passengers for the shift from a walking posture to a floating one. The entire system must feel intuitive, where a journey from a home to a zero-gravity workshop is as simple as a subway transfer, a seamless transition between different states of being within a single, engineered world. This connective tissue of transit does more than move objects and bodies. It defines the rhythm of daily life, making a vast, artificial geography feel intimate, immediate, and whole. The silent hum of this engineered world is not just the flow of air or the thrum of machinery. It is the sound of constant, invisible stewardship. An asteroid habitat of this scale cannot be managed by human hands alone. The sheer volume of repetitive, dangerous, and precision tasks would overwhelm even the most dedicated colony. Its survival depends on an army of autonomous machines, a hierarchy of synthetic guardians working in seamless concert to maintain the bubble of life within the stone. These are not the humanoid robots of science fiction, but specialized tools evolved for a specific, brutal environment. On the exterior, clinging to the rocky surface like metallic insects, spider-like prospecting drones would endlessly scan and sample, their articulated legs navigating treacherous terrain to identify new veins of ice or metal ore for extraction. Inside the caverns during construction, swarms of robotic welders, guided by a shared digital blueprint, would move along pre-programmed paths, their arcs of light fusing structural members with a precision no human in a bulky suit could ever match. And when the habitat is complete, a smaller cast of maintenance bots takes over. These would be the meticulous inspectors, equipped with sensitive lasers and thermal cameras, crawling along the vast interior shell or traversing the exterior shielding in search of the tiniest stress fracture or the faint scar of a micrometeoroid impact, repairing breaches before they ever become a threat to the atmosphere. Yet the true nerve center of this operation is not a physical robot, but the distributed artificial intelligence that manages the habitat's metabolism. This AI acts as the colony's autonomic nervous system, processing torrents of data from 10,000 sensors. It monitors the delicate balance of oxygen and carbon dioxide in the air, adjusting the flow to algae bioreactors with imperceptible tweaks. It watches the ebb and flow of power from solar arrays, seamlessly switching between battery storage, thermal banks, and reactor output to ensure not a single light flickers. It oversees the entire resource processing chain, from ice extraction to metal refining, optimizing each step for maximum efficiency and minimum waste. This system makes millions of micro-adjustments every hour, a silent symphony of corrections that maintains the environment in a state of perfect, dynamic equilibrium. This level of automation does more than just keep the lights on. It fundamentally redefines the human role. Freed from the burdens of routine maintenance, hazardous repairs, and tedious monitoring, the colonists are not idle. Their purpose shifts upward toward the uniquely human domains that machines cannot replicate. They become the researchers probing the asteroid's primordial secrets, the engineers designing the next generation of habitats, the artists and teachers shaping a new culture, and the governors navigating the complex social contracts of a closed society. Their work is one of oversight, creativity, and exploration, not manual labor. In this way, the habitat transcends being merely a structure. It becomes a living machine, a single vast organism whose immune system is made of scanning drones, whose circulatory system is managed by algorithms, and whose steady breath is maintained by silent, tireless guardians. This symbiosis between human and machine is not a luxury. It is the essential partnership that makes a civilization inside a rock not just possible, but sustainable for generations to come. The true test of this engineered world is not its machinery, but its people. Who will choose to live inside a hollowed mountain, and more importantly, how will they live together? The societal blueprint for an asteroid colony is as critical as its life support schematics, a delicate form of social engineering for a small, isolated community where every conflict carries the weight of collective survival. The first pioneers will not be passengers. They are integral components of the system, selected and trained with a rigor that matches the construction of the habitat itself. Technical expertise in botany, engineering, or medicine is only the baseline. Psychological screening would seek individuals with exceptional emotional resilience, a proven ability to cooperate under prolonged stress, and a genuine commitment to a communal lifestyle where privacy is limited and individual actions directly impact everyone's safety. These are not just scientists on a mission, they are the founding citizens of a new world, and their social cohesion is the final, crucial layer of infrastructure. Governance in such a closed environment cannot be an afterthought. Traditional Earth-based models, built for populations of millions with ample resources and space, may fracture under the intense pressure of a sealed society. Early models might lean toward a direct democracy, where every colonist has a vote on major resource allocations or habitat regulations, fostering a strong sense of ownership and shared destiny. Yet, the complexity of managing the colony's life support and industrial systems could also necessitate a technocratic council, where key decisions are informed by those with the deepest understanding of the interconnected systems. ensuring technical necessities are not overruled by short-term social pressures. We might even see novel systems emerge, enabled by transparent digital ledgers, where every unit of water processed, every kilowatt of energy generated, and every gram of metal alloyed is accounted for in a shared, immutable record. This radical transparency in resource allocation could prevent grievances and build universal trust in the fairness of the system, as every citizen could see exactly how the colony's lifeblood is being used and shared. Beyond governance, daily social structures would need to consciously cultivate cooperation. Skill sharing would be woven into the fabric of life, where a structural engineer might also teach basic hydroponics, and a doctor might learn reactor maintenance protocols. This cross-training does more than provide redundancy. It builds empathy and mutual respect across specialties, reinforcing that every role is vital. Conflict resolution mechanisms would be established from day one, not as a sign of anticipated failure, but as a recognized necessity for maintaining group health. These might include mandatory mediation sessions, communal forums for airing concerns before they fester, and clear, agreed-upon protocols for resolving disputes that threaten operational safety. The goal is to design a social environment that, like the habitat's environmental systems, is self-correcting and resilient. Establishing this stable society is the ultimate act of creation. It moves the project from a feat of engineering to the birth of a civilization. The first children born in the habitat will inherit not just a technological marvel, but a social contract written in the stark reality of interstellar isolation. Their sense of normal will be one of profound interdependence, where individual liberty is balanced against collective responsibility in a way no earthbound society has ever required. The success of their home will depend as much on the strength of their community bonds as on the integrity of their radiation shielding. This final layer, the human layer, asks the most profound question of all: can we design not just a place to survive, but a way of life worth sustaining among the stars? This economic independence is the spark for something far greater. A fully operational asteroid habitat would not merely sustain itself, it could become a powerhouse of the new space economy, transforming from a closed survival capsule into an open interstellar marketplace. Its unique position and resources position it for roles no planetary base can easily fill. First, it is a natural manufacturing hub. The combination of abundant raw materials and the pervasive microgravity environment at its central axis unlocks production possibilities impossible on Earth. In that gentle, persistent free fall, metals can be alloyed with perfect uniformity, creating super-strong, defect-free materials for spacecraft hulls. The same environment allows for the flawless growth of ultra-pure semiconductor crystals, the kind needed for the most advanced computing systems. This habitat could become a factory for the very technologies that enable further exploration, selling high-value components to lunar outposts or Martian settlements. Its second major role is as a refueling depot, a cosmic gas station along the celestial highways. By cracking water ice into hydrogen and oxygen propellant, it can sell the most precious commodity in space, delta V, the ability to change trajectory. A mission from Earth to Mars could launch with minimal fuel, dock at the asteroid habitat to top off its tanks from locally produced stores, and then continue its journey with a full load. This drastically reduces the initial mass launched from our planet's deep gravity well, making deep space travel far more economical and frequent. The habitat itself would use this same fuel to send out its own mining drones to nearby asteroids, constantly expanding its resource base and industrial capacity. Beyond industry and logistics, the habitat offers a unique environment for pure science. Shielded from Earth's magnetic field and atmospheric interference, its laboratories could peer into the universe with unprecedented clarity. Physicists could conduct experiments in sustained zero gravity to probe the fundamental forces, while biologists could study the long-term effects of artificial ecosystems and partial gravity on genetics and development, research critical for humanity's future on other worlds. This makes the colony a magnet for researchers, adding intellectual capital and innovation to its economic portfolio. And then there is the experience economy. For those who can afford the journey, a visit to an asteroid habitat would be the ultimate tourist destination, offering vistas found nowhere else. Guests could experience the surreal sensation of walking in a lush, park-filled cylinder where the ground curves upward around them, or float in the central microgravity hub, looking out viewports at the raw, primordial landscape of the asteroid's exterior. This tourism would not be frivolous. It would be a vital source of external revenue and a bridge for cultural exchange, reminding Earth of the tangible wonder taking shape in the deep. These interconnected roles, manufacturing, refueling, research, and tourism, weave the asteroid habitat into the fabric of a growing interplanetary society. It becomes a central trading node, exchanging refined metals for lunar helium-3, sending advanced computer parts to Mars, and receiving specialized crops or cultural goods in return. This economic web is what ultimately transforms the vision from a government-funded survival experiment into a self-sustaining, expanding frontier of human enterprise. The habitat's success would no longer be measured just in air and water recycled, but in contracts fulfilled, discoveries made, and connections forged across the solar system, proving that life inside a rock can mean thriving at the very heart of a new economic dawn. But this humming engine of life and industry has a hidden byproduct, a silent tide that threatens to drown the entire system from within. Every watt of power used, from the glow of a single light to the roar of a smelting furnace, does not vanish. It transforms inevitably into waste heat. In the sealed, airless world of an asteroid habitat, this heat has nowhere to go. Without the open sky and atmosphere of a planet to absorb and radiate it away, the interior would slowly, inexorably become an oven. Mastering this thermal balance is not a secondary system. It is a continuous battle against the laws of thermodynamics, demanding an architecture of cooling on a staggering scale. The primary weapon in this battle is the radiator, a technology that feels almost primitive in its simplicity yet must be engineered to perfection. Picture massive, wing-like structures unfurling from the asteroid's surface or extending on long, skeletal booms away from the habitat. These are not solar panels, they are emissive surfaces, often painted a deep, matte black to maximize their ability to shed infrared radiation. They glow with an invisible light, the heat of civilization bleeding off into the endless cold of space. Their design is a constant compromise. To be efficient, they need immense surface area, but every square meter is vulnerable to micrometeoroid puncture. Engineers might design them as redundant, segmented panels, so a strike on one fin does not cripple the entire thermal system. Some concepts even propose liquid droplet radiators, where a stream of tiny, hot fluid droplets is ejected into space to radiate heat before being recaptured and cooled, creating a cloud-like cooling system that is less vulnerable to solid impact. Inside the habitat, the thermal challenge is more nuanced. You cannot simply let heat accumulate in a server room or a manufacturing bay. Instead, a sophisticated circulatory system moves warmth like a bloodstream. Networks of fluid-filled pipes, akin to a building's plumbing but for temperature, would snake through the walls and floors. These loops would actively gather excess heat from machinery, computers, and even the densely packed human bodies in communal spaces. But this captured thermal energy is not just waste, it is a resource to be redirected. This warm fluid can then be pumped to areas that need heating, such as agricultural tiers during their simulated night cycle, or through radiant floors in residential sectors to maintain a comfortable ambient temperature without using extra electricity. It is a dynamic, intelligent redistribution of energy, ensuring no watt is truly wasted. The ultimate goal is a state of equilibrium, where the heat generated by 10,000 processes matches the heat radiated away by those silent, black wings into the void. A failure in this balance is not a sudden explosion, but a slow, suffocating creep. Temperatures would rise by a fraction of a degree each day, stressing life support systems, reducing machine efficiency, and pushing the human inhabitants toward heat exhaustion. The radiators, therefore, are more than just cooling panels. They are the habitat's lifeline to the cosmic cold, the essential release valve for its own vibrant metabolic heat. Their silent operation is the final, non-negotiable requirement for permanence, ensuring the world inside the rock remains a temperate garden and not a tomb sealed by its own vitality. A single hollowed asteroid is a seed, not the final harvest. The true power of this engineering lies in its potential for exponential growth, a blueprint for scaling humanity's presence from solitary habitats into sprawling, interconnected archipelagos among the stars. The first successful colony provides more than shelter. It provides a proven toolkit and a functioning factory. With its industrial capacity established, it can look outward to its celestial neighbors. Newly arrived asteroids, nudged into stable orbits nearby, become the raw material for expansion. Instead of hollowing each one entirely, specialized processing outposts could dismantle them, feeding a steady stream of refined metals, glass, and volatiles into space-based shipyards. Here, in the gentle embrace of microgravity, these asteroid-derived materials are fashioned not into more mountains, but into standardized habitat modules, power satellites, and docking hubs. These new structures could then be linked to the original colony with pressurized tunnels, creating a growing, modular complex where different sections specialize in research, manufacturing, or agriculture, all interconnected like the neighborhoods of a vast, three-dimensional city. This is the natural progression from a single homestead to a thriving town, built from the resources of the frontier itself. This scalable logic points toward even grander visions, concepts that once lived only on paper, like the Kalpana 1 or the classic O'Neill cylinder. These are not hollowed asteroids, but purpose-built megastructures, cylinders miles in length that rotate to provide Earth-like gravity across their entire inner surface. Constructing such behemoths from materials launched from Earth is an economic fantasy, but constructing them from the metal and stone of the asteroid belt changes the equation entirely. The first generation of asteroid habitats becomes the industrial base to make these dreams tangible. They would serve as the construction sites and workforce hubs, building the massive skeletal frames of these cylinders piece by piece from mined and smelted asteroidal iron, spinning them up and then filling their vast interiors with soil, water, and atmosphere also wrested from countless space rocks. The technologies perfected in that first rocky home, the closed-loop life support, the radiation shielding, the artificial gravity management, become the foundational code for these larger, more ambitious worlds. The ultimate destination of this path is a transformation of the solar system's economy and ecology. We could envision not just a few habitats, but a network of thousands, a swarm of human-made worlds orbiting the sun, each home to millions of people. The asteroid belt, rather than a barren field of rubble, becomes a quarry, a lumberyard, and a wellspring for an entirely space-borne civilization. This scalable future means that humanity's growth is no longer tethered to the finite surface of Earth. Our presence expands in proportion to our ability to process and build, using the abundant materials that already float in the void. The first hollowed asteroid, therefore, is the most difficult step, the proof of concept for a process that can, in theory, repeat itself almost without limit. It answers a profound question about our destiny, suggesting that our future among the stars is not about finding another Earth, but about learning the deep art of building new ones from the cosmic raw materials all around us. Yet this monumental technical achievement rests on a foundation of questions that cannot be solved with engineering alone. The moment we begin to alter a celestial body, we step onto a new ethical frontier, one governed by treaties written for a different era and responsibilities we are only beginning to understand. At the heart of this lies the Outer Space Treaty of 1967, a landmark document that forms the bedrock of international space law. It declares that space is the province of all humanity, not subject to national appropriation by claim of sovereignty. This noble principle, however, collides with practical reality when we consider the act of hollowing out an asteroid. If a company or nation spends trillions to transform a space rock into a habitable world, who owns it? The treaty forbids claiming the asteroid itself, but is silent on the structures built upon or within it. This legal gray area has sparked intense debate, with some arguing that the right to use resources, as affirmed by more recent national laws, implies a kind of de facto ownership of the improved asset, while others insist any permanent habitat must remain a commons accessible to all humankind. Resolving this tension is not a bureaucratic footnote. It is essential for attracting the investment needed to make such projects real, while preventing a chaotic, conflict-ridden land grab in the solar system. Parallel to ownership is the profound scientific responsibility of planetary protection. Every asteroid is a frozen time capsule, holding chemical and possibly even probiotic clues to the formation of our solar system over 4.5 billion years ago. The process of hollowing one out for habitation is, by its nature, destructive. Mining operations could obliterate pristine stratigraphic layers that record the early history of our cosmic neighborhood. This forces a difficult prioritization. Must every asteroid remain an untouched museum piece, or can we designate some for development while preserving others as protected scientific reserves? The answer likely lies in careful prospecting and international agreement, ensuring that the drive to build new homes does not forever erase the oldest chapters of our own story. Equally critical are the biological risks that flow in both directions. Forward contamination is the concern that we might inadvertently carry hardy Earth microbes to the asteroid on our tools or spacecraft. If these organisms found a niche within the asteroid's ices or minerals, they could not only compromise the search for any potential native extraterrestrial organics, but could also trigger unpredictable changes in the material we intend to use for life support. Conversely, back contamination, while less likely from an asteroid, involves the hypothetical risk of bringing an unknown extraterrestrial substance or organism into a closed habitat with unknown effects on its carefully balanced biosphere. These are not science fiction fears, but operational protocols that space agencies already follow for robotic missions to Mars. Scaling these protocols to the level of industrial asteroid modification will require entirely new standards of cleanliness and quarantine, treating the entire construction process as both an engineering and a biological containment project. Establishing clear, fair, and forward-looking frameworks for these issues is a challenge of diplomacy and vision equal to the physical engineering. It demands unprecedented international cooperation, creating new agreements that balance the right to use space resources with the duty to preserve humanity's common scientific heritage and ensure safety. This legal and ethical architecture must be built with foresight, ideally before the first mining drill touches regolith, to guide the peaceful and responsible development of this new frontier. The success of our off-world future depends not just on our ability to reshape rock, but on our wisdom to govern the transformation with a sense of shared destiny and profound respect for the cosmos we are entering. The bridge between today's blueprints and that hollowed mountain is built not by a single leap, but by a careful sequence of footsteps. We must first prove every radical technology on a modest, manageable scale, through a series of precursor missions designed to de-risk the grand vision one experiment at a time. The journey begins not with a mining fleet but with a sophisticated robotic scout. This spacecraft, far more advanced than any previous asteroid probe, would rendezvous with a carefully selected target and enter a close, stable orbit. Its mission is to perform an unprecedented physical examination. Using ground-penetrating radar, it would map the asteroid's internal structure in 3 dimensions, distinguishing solid bedrock from loose rubble piles with centimeter-scale resolution. A suite of seismic sensors, perhaps deployed by small penetrators fired into the surface, would listen to the asteroid's response to controlled impacts, building a detailed picture of its structural integrity and composition at depth. This scout would not just look, it would touch and taste, using robotic arms to collect samples from multiple sites, analyzing them with onboard laboratories to confirm the precise mix of water, metals, and organics. This mission alone could take years, but the data it returns would be the definitive engineering survey, turning a promising candidate from a distant dot of light into a known, quantifiable construction site. With a target fully characterized, the next step moves from observation to action, testing the core processes of resource extraction in the actual space environment. One logical venue for these initial trials is a dedicated orbital facility, perhaps a module attached to the International Space Station or a free-flying platform. Here, in the persistent microgravity of low Earth orbit, engineers could conduct benchtop-scale experiments with real asteroid simulant material. Robotic arms would practice the delicate maneuvers of drilling into a granular surface without pushing the spacecraft away. Small furnaces heated by concentrated sunlight or microwaves would test methods for extracting water vapor from clay or smelting metallic grains. The goal is not to process tons of material, but to perfect the choreography of each step, to see how materials behave in vacuum and zero-G when heated, cut, or manipulated, and to refine the designs of the tools that will one day do this work autonomously millions of miles from Earth. Each successful small-scale test builds confidence in the underlying physics and robotics, identifying problems that are easy to solve in a workshop but could be catastrophic on a distant asteroid. The most dramatic Precursor mission might be a full-scale demonstration of the inflation technique. Imagine a spacecraft traveling to a very small asteroid, perhaps just 10 meters across, or even capturing a sizable boulder and bringing it into a stable orbit. Instead of hollowing it out, the mission would aim to modify it. The spacecraft would drill a narrow shaft into the rock's center and insert a durable, flexible bladder. Then, with the world watching, it would begin to slowly inflate. Sensors covering the asteroid's surface would monitor every tiny fracture and shift, measuring exactly how much pressure is required to expand the cavity and how the surrounding material compacts. This mission would answer fundamental questions. Does the rock form a stable, cohesive shell as theory predicts, or does it fragment unpredictably? The data would validate or reshape our entire approach to creating large-scale spaces, providing empirical proof for what has so far been only sophisticated computer modeling. A successful inflation test would be a monumental milestone, a tangible demonstration that we can indeed persuade a space rock to become a vessel. These incremental missions are the indispensable scaffolding for the mega-project. A robotic scout de-risks the selection, orbital processing experiments de-risk the extraction technology, an inflation demonstrator de-risks the construction method. Each one solves a handful of specific, critical problems, retiring unknowns and replacing them with hard-won knowledge. They build not just technology, but something equally vital, institutional experience. Space agencies and private companies would learn how to manage multi-year campaigns of remote robotic construction, developing the deep operational expertise needed for the far more complex endeavor. This phased approach transforms an awe-inspiring but seemingly impossible vision into a series of difficult but achievable engineering challenges. It charts a credible path from the laboratories and workshops of today to the day when humanity can point to a spinning mountain in the sky and say, with certainty, that we know how to make it a home. The health of a society built inside a spinning world is a science of its own. Even with a perfect simulation of Earth's gravity, the body does not forget it is living inside a machine. The subtle, persistent pull of Coriolis forces, the same effect that makes tossed objects curve, works on our physiology in ways we are only beginning to model. For the inner ear, the organ of balance, this constant background force could create a low-grade sensory conflict, a whisper of disorientation that some may never fully shake off, potentially leading to a higher baseline of motion sensitivity or nausea in a subset of the population. More critically, doctors would need to study how these forces influence the complex hydraulics of our circulatory system. Does blood flow differently in a rotating vessel? Could it lead to unforeseen pressures on the heart or contribute to novel patterns of vascular stress over decades? The medical bay in an asteroid habitat is not just a clinic, it is a frontline research laboratory where every routine checkup contributes data to a grand, long-term study on human adaptation to engineered gravity. This necessitates medical facilities of extraordinary versatility. A surgical suite, for instance, must account for the habitat's spin. The delicate act of surgery relies on an intuitive understanding of how fluids and tissues behave under gravity. In a rotating frame, even the flow of blood from an incision or the drape of a sterile cloth could follow a slight, predictable curve. Surgeons and their robotic assistants would need training to internalize this new physical reality, and equipment would be calibrated to account for it. Beyond trauma, the closed-loop nature of the environment presents a heightened risk from contagious illness. An aggressive virus or bacterium introduced by a new arrival or emerging from a mutation could spread with alarming efficiency through the shared atmosphere and recycled water. Therefore, medical infrastructure is deeply integrated with the habitat's life support. Advanced multi-stage air filtration systems using HEPA and ultraviolet sterilization would run continuously, and any new arrivals would undergo strict quarantine in isolated modules with separate air handling before joining the general population. The entire colony operates with the underlying principle of planetary scale hygiene. Ensuring wellness, therefore, becomes a proactive, continuous endeavor rather than a reactive one. A new branch of medicine, perhaps called rotational habitat medicine or enclosed world physiology, would emerge. Its practitioners are part physician, part public health engineer, and part systems ecologist. They monitor not just individual vital signs, but the health indicators of the habitat itself, the bacterial load in the water reclamation system, the air quality metrics in different districts, and the psychological well-being surveys of the community. Their tools include genetic sequencers to rapidly identify pathogens, telemedicine links to specialists on Earth, and a deep understanding of how every environmental parameter, from light spectrum to atmospheric pressure, interacts with human biology. The goal is to anticipate problems before they manifest, to tweak the environment itself as a form of preventative care. In this way, the doctor's role expands from healing the individual to stewarding the collective health of a miniature, fragile biosphere, where every cough echoes through the entire interconnected world. The culture that blooms inside the rock will be its own form of life support. Isolated from Earth, shielded by distance and time delay, an asteroid community cannot simply import its identity. It must grow one from the soil of its unique existence. This cultural evolution is not a leisurely pastime. It is a vital organ for the society's long-term health, a way to process the profound experience of living in a handmade world. The art born here will speak a new language. Visual artists might not paint forests or oceans they have never seen, but instead capture the haunting beauty of their interior cosmos. Their canvases could depict the vast, curving parklands under the artificial sun strip, the intricate dance of maintenance drones against the shell like metallic fireflies, or the abstract, mesmerizing patterns of fluid dynamics in the low-gravity core. Sculpture would interact intimately with the habitat's geometry, works designed to be viewed from a moving maglev car, or that change meaning when seen from different levels of the gravity gradient. The very walls of public spaces could become living murals, displaying slow-motion feeds from the surface telescopes or generative art that visualizes the real-time data of the life support systems, turning the colony's heartbeat into a public aesthetic experience. Music and sound would be fundamentally reshaped by the environment. The acoustics of a rotating cylinder are unlike anything on Earth, with sounds potentially carrying in unusual ways along the curved surfaces. Composers might write pieces specifically for the central atrium, where the lack of a true ceiling creates a unique reverberation, or design soundscapes that incorporate the ever-present, soothing hum of the air processors and water recyclers, weaving the ambient noise of survival into symphonies. Storytelling becomes the primary vessel for history and values. The epic tales will not be of ancient heroes on battlefields, but of the first excavation, the stories of the engineers who sealed the first major breach, or the botanist who cultivated the first successful orchard from asteroid-derived nutrients. These narratives reinforce the core tenets of the community: interdependence, resilience, and the sacredness of their closed-loop world. New traditions would crystallize around the habitat's own rhythms, celebrating the anniversary of achieving atmospheric closure, or holding a festival of light when the external solar arrays reach their annual peak efficiency. Even entertainment and sport would be reinvented by the physics of the home. In the low-gravity hub, three-dimensional sports could emerge, a kind of free-fall acrobatics played in spherical arenas where players push off from all surfaces. On the outer shell, where gravity holds, traditional sports would be modified, but a game like soccer would have to account for the subtle, constant curve of the playing field. The most popular spectacles might combine physical prowess with technical skill, such as races involving modified maintenance exoskeletons or competitions to program drones for the most elegant construction ballet. These activities do more than pass the time. They embody the community's mastery of its environment, turning the challenges of their world into sources of joy and communal pride. This cultural crucible is where survival transcends into meaning. The shared creative expressions, the unique games, the holidays born of their own history, all forge a powerful collective identity. A child growing up here will feel a deep, innate connection to the hum of the machines and the curve of the sky, not as limitations, but as the foundational elements of their homeland's soul. This internal culture becomes the psychological gravity that holds the society together, a force as critical as the spin-induced pull beneath their feet. It answers the silent question of why they are there, not just to endure, but to build a new chapter of human expression, one shaped entirely by the stars. But the purpose of these hollowed worlds could be far grander than expansion or economy. It could be about preservation, about creating the ultimate backup for everything we hold dear. An asteroid habitat sealed within its mountain of stone and spinning in the void represents one of the most secure environments imaginable in our solar system. This inherent security points to a profound secondary mission, transforming these engineered spaces into arks, not just for people, but for the biological and cultural heritage of an entire planet. This shifts the entire endeavor from a story of colonization to one of cosmic stewardship, adding a layer of deep moral weight to the technical blueprints. Imagine a dedicated chamber within the habitat, maintained at a constant cryogenic temperature. Here, in vaults designed to survive for millennia, rest the genetic seeds of Earth. Not just the crops we rely on, but the full tapestry of life, from the smallest microbe in the soil to the majestic creatures of forest and ocean. This is a living library of deoxyribonucleic acid, a biological backup drive for the planet's biodiversity. Should a catastrophe, natural or otherwise, severely damage Earth's ecosystems, these genetic archives would offer a path to restoration, a chance to rebuild complex webs of life from their fundamental code. The asteroid arc becomes a silent guardian of genetic possibility, ensuring that 1,000,000 unique threads of evolution are not lost to a single point of failure on our home world. Alongside this library of life would reside the library of the human mind, digital servers shielded by the same rock that protects the inhabitants could hold the sum of our knowledge, art, and history. Every great novel, every symphony, every scientific paper, every photograph of a sunset or a child's smile, every language and cultural tradition could be encoded and stored in redundant, radiation-hardened systems. This is not merely a data dump, it is the collective memory of our species curated and preserved against the possibility of a dark age. Future generations, whether they live on Mars, in orbital cities, or right here on Earth, could access this repository to understand where they came from, to relearn lost skills, or to simply experience the beauty created by their ancestors. The arc safeguards the continuity of culture itself. The concept extends even to physical artifacts. While mass is precious, select items of immense cultural significance, perhaps digitally scanned in perfect detail for replication, could find a place. A seed from the oldest living tree, a fragment of parchment from a foundational text, or a simple tool that tells the story of human ingenuity, these objects carry a tangible connection to our past that pure data cannot fully convey. Their presence in the ark would serve as a powerful reminder of the world that gave birth to the civilization now living among the stars, a touchstone of origin and identity. This vision transforms the hollowed asteroid from a potential new home into a sacred trust. The engineering challenges of radiation shielding, power stability, and perpetual maintenance take on a new gravity when the purpose is to preserve the legacy of a world for 10,000 years, not just sustain a population for a century. It demands systems with even greater redundancy, materials chosen for longevity over efficiency, and a design philosophy centered on passive survival. The ark must be built to outlast its builders, to remain silent and secure through epochs, waiting for a day its treasures may be needed, but hoping profoundly that they never are. In this light, the act of hollowing the asteroid becomes one of the most profound expressions of foresight our species could undertake. It is an acknowledgement of both our fragility and our responsibility. We are not just building shelters for ourselves, we are constructing a vault for the very essence of our blue planet, ensuring that life, in all its magnificent diversity and creativity, has a chance to endure no matter what storms the future may bring to our celestial cradle. The very act of building this world will forge the tools for its own transformation. Deep within the asteroid's processing plants, under the pure vacuum and persistent microgravity of space, we will not just use materials, we will reinvent them. This environment is a pristine laboratory unlike any on Earth, free from the contamination of air and the distorting pull of strong gravity. Here, metals can be mixed in ways previously impossible. On our planet, melting metals requires a crucible, a container that inevitably leaches its own atoms into the molten mix, introducing impurities that weaken the final alloy. But in the void, a technique called containerless processing becomes possible. Using carefully tuned electromagnetic fields, blobs of molten iron, nickel, and cobalt extracted from the asteroid can be suspended in mid-air, floating without ever touching a foreign surface. They can then be merged, their atoms combining in a perfectly pure dance, cooled and solidified into alloys of unprecedented strength and uniformity. These space-forged metals could be hundreds of times stronger than their terrestrial counterparts, yet remarkably lightweight, the ideal skeleton for future habitats or the hulls of ships destined for the outer planets. Beyond metals, the most common substance in the asteroid, the dusty regolith itself, holds a different kind of promise. This fine, abrasive powder is often seen as a nuisance, but under the focused eye of a sunbeam, it becomes the feedstock for a new age of ceramics. The process is called optical sintering. Imagine large, curved mirrors concentrating the unfiltered sunlight of space into a precise, intense beam. This beam scans over a bed of carefully leveled regolith dust, not melting it, but fusing the particles at their boundaries. Layer by layer, it builds up solid objects, from intricate machine parts to massive structural blocks, directly from the dust of the asteroid. The resulting material is not like traditional pottery. It is a novel, glassy ceramic with exceptional thermal stability and resistance to radiation, perfect for lining furnace interiors or shielding sensitive electronics. We could even tweak the composition, adding traces of different minerals to create transparent panels for viewports or fibers for weaving cables stronger than steel. This material science revolution is born from stark necessity, the need to build and repair everything on site with what is available. Yet its implications ripple far beyond the habitat's rocky walls. The super-strong, lightweight composites and novel ceramics invented in these zero-gravity workshops would become incredibly valuable exports. Think of a new alloy perfected in space that could make Earth-bound airplanes 40% lighter, slashing fuel consumption and emissions. Envision a transparent ceramic forged from asteroid dust that allows skyscrapers to harness sunlight more efficiently or enables safer, more durable batteries for electric vehicles. The asteroid habitat, in its struggle to survive, inadvertently becomes the cradle for the next industrial revolution, sending back not just resources, but radical new recipes for matter itself. The workshop where we learn to build homes from cosmic rubble may well become the factory that reshapes the material foundation of our civilization on Earth. This radical self-sufficiency creates more than survival. It forges a new environmental conscience. Locked inside a finite bubble of rock and air, the colonists cannot afford the concept of waste. Every byproduct, every scrap, every joule of heat is a vital thread in the fabric of their world, to be rewoven, not discarded. This necessity births an ethos of profound circularity, a model of sustainability so pure it could only be born from the stark constraints of space. The habitat's economy is not linear, a straight line from extraction to disposal. It is an endless, elegant circle. Take a simple meal. The organic waste from food preparation is not thrown away. It is collected and fed into anaerobic digesters. These sealed tanks, filled with specialized bacteria, break down the material, producing two valuable outputs. The first is a nutrient-rich slurry, a perfect fertilizer that is piped directly back to the hydroponic farms to nourish the next generation of crops. The second is biogas, primarily methane, which can be burned in generators to supplement the power grid or used as a feedstock for manufacturing plastics and other polymers. The inedible parts of plants, the stems and roots, might be processed into biodegradable materials for packaging or clothing fibers. In this system, the end of one cycle is the literal beginning of another. This principle extends to the inorganic world with even greater rigor. A broken component from a manufacturing robot is not a piece of trash. It is a source of refined material. It would be scanned, disassembled by automated systems, and sorted. Its metals are melted down and realloyed. Its plastics are chemically broken back into their base polymers for reuse. Even the lubricants and coolants that keep machinery running are filtered and regenerated in a continuous loop. never vented to the environment because there is no external environment to absorb them. The very dust that settles in a corridor is periodically gathered, analyzed, and fed back into the appropriate reclamation stream. The habitat's entire industrial metabolism is designed for near-perfect recovery, driven by the simple, unyielding logic that every atom imported from the asteroid is precious and irreplaceable. This hyper-efficiency is not driven by ideology, but by the brutal mathematics of isolation. There is no landfill over the horizon, no atmosphere to safely dilute chemical emissions, no oceans to absorb excess heat or runoff. The feedback loop between action and consequence is immediate and inescapable. If a process creates a toxic byproduct, you cannot pipe it away. You must deal with it inside your own home. This forces a fundamental shift in design philosophy called cradle-to-cradle thinking. From the moment an object is conceived, its entire life cycle is planned. Engineers ask, how can every part of this be easily disassembled? What materials will allow for the cleanest recycling? How can its function be fulfilled with minimal energy and maximal longevity? This mindset, born of survival, eliminates the very idea of planned obsolescence. Things are built to last, and when they finally do wear out, they are built to come apart cleanly and rejoin the resource pool. The asteroid habitat, therefore, becomes a living prototype for a civilization that exists in a state of dynamic equilibrium with its environment, because its environment is itself. It demonstrates that a high-tech, advanced society does not have to be a burden on its world. It can be an integrated, harmonious part of a closed loop. This is perhaps the most profound lesson to beam back to Earth. Our planet, for all its vastness, is also a closed system, a fragile bubble of life adrift in a cosmic void. We have simply been slow to feel the walls. The asteroid colony, by magnifying those constraints to an extreme, shows us a possible path forward, a blueprint for a future where human ingenuity is measured not by what we can extract, but by how perfectly we can sustain. The dream of a hollowed asteroid home is not a single leap, but a century-long relay. We can map a plausible path from our current blueprints to a completed habitat, not as a firm prediction, but as a sequence of logical, escalating phases. The first runners are already on the track. The next 2 decades, the 2030s and 40s, will belong to the robotic scouts. These missions will be far more ambitious than the sample return probes of today. Their goal is not to grab a handful of surface material and leave, but to move in and conduct a full geological survey. Think of them as autonomous prospectors and structural engineers combined. They will orbit their target for years, using advanced radar and seismic thumpers to build a 3-dimensional map of the asteroid's interior, distinguishing solid core from loose rubble pile. They will drill, sample, and analyze on site, confirming the precise abundance of water, metals, and organics. In parallel, in the microgravity laboratories of lunar orbit or dedicated space stations, we will perfect the tools of the trade. Small-scale experiments will demonstrate how to extract water from simulated regolith using solar ovens, how to sinter dust into solid blocks with focused light, and how to manage the chaotic plume of debris created by drilling in a vacuum. These are the essential, unglamorous steps that retire risk, turning theoretical processes into proven, repeatable operations. By the middle of the century, the 2050s, we could witness the first human footsteps on a carefully selected near-Earth asteroid. This would not be a brief flag-planting visit, but a sustained mission of months, perhaps even a year or 2. The crew's primary objective would be to begin the transformation. They would oversee the deployment of the first stabilization thrusters, beginning the slow, meticulous process of stopping the asteroid's tumble and imposing a controlled spin. They might supervise robotic teams as they drill the first pilot tunnels or deploy the initial anchors for a large-scale net, securing the construction site. This phase is about laying the physical and operational groundwork, proving that humans can direct complex, long-duration engineering tasks in the deep space environment, far beyond the comforting proximity of the Moon. If those missions succeed, the final decades of this century could see the birth of the first true habitat. Between the 2080s and the year 2100, the first permanently inhabited, partially hollowed asteroid could become operational. This would not be a vast, city-sized cylinder, but a pioneering outpost. Imagine a cavern space roughly the volume of a large sports stadium, sealed, pressurized, and powered. Its life support systems would be a closed loop, its walls lined with the first generation of artificial gardens. The initial population might be small, perhaps a few dozen engineers, scientists, and technicians. Their lives would be a continuous experiment, monitoring the health of their handmade world while expanding its capabilities. They would process local material to add new modules, thicken radiation shielding, and slowly increase the size of their agricultural base. This outpost is the proof of concept, the demonstration that the radical engineering chain from selection to habitation actually works as an integrated whole. The vision of full-scale cities with populations in the thousands or millions is almost certainly a project for the 22nd century. It would require the industrial output of that first outpost to bootstrap the construction of far larger structures, or the coordinated effort of multiple habitats working in concert. This timeline stretches across generations, a project for our grandchildren and their children. Yet, its very plausibility is rooted in the sequential nature of the challenges. We are not waiting for a single magical invention. We are looking at a staircase of technologies, each step building on the last. Robotic prospecting extends current planetary science. In-situ resource utilization demonstrations are already in early planning. Crewed deep space missions are the stated goal of major space agencies. The timeline is long, but the direction is clear. It transforms the idea from pure science fiction into a grand, multi-generational engineering project, a destination on a map of the future we are already beginning to draw. This grand tapestry of engineering and imagination weaves together a future written not on paper, but in the very fabric of the cosmos. The vision of hollowing out asteroids for human habitation stands as one of the most audacious challenges ever conceived, a symphony of disciplines where planetary science conducts the orchestra of robotics, materials engineering, and social design. We have journeyed from the critical act of choosing the perfect cosmic quarry to the profound questions of what culture might bloom within its shielded, spinning heart. This pursuit is about far more than mere survival in a hostile void. It is a proactive declaration, an intentional step toward building a resilient, multi-planetary future for humanity. It represents a fundamental shift in perspective, learning to see the dangers of space not as barriers, but as raw materials for growth, and the emptiness between worlds not as a desert, but as a field ripe for sowing new homes. The obstacles before us are undeniably staggering. They demand solutions to problems of physics and psychology we are only beginning to formulate. Yet, history shows us that each towering challenge is, in its essence, a frontier for innovation waiting to be mapped. Containing a catastrophic collapse while carving a mountain, forging an atmosphere inside a stone, designing a society where every action echoes through a closed loop, these are not dead ends. They are invitations. They call upon the very best of our ingenuity, our capacity for patient, long-term thinking, and our ability to cooperate across generations and borders. As we look to the stars, let this vision inspire more than passive wonder. Let it ignite a renewed commitment to the tools we will need to make it real, relentless curiosity, unwavering perseverance, and a spirit of shared enterprise that looks beyond any single nation or era. The mountain waits silent and ancient, holding within its rocky heart the potential for a new chapter in the human story. The most exciting question is no longer if we can do it, but what we will become in the trying.